Okay, I'll give you 10 more seconds. Group 1, challenge 3. Otherwise, group 2, challenge 3. You guys get ready.
Teacher, I think it's probably challenge 2.
Oh, you're right. You're right. You're right. You're right. Okay, challenge 2. You're right. Challenge 2. Challenge 2.
Okay,
Sorry, my
so
fault. Challenge 2, group 1. Sorry, go ahead, guys. Because we started counting from 0, so I lost track. Go ahead.
can you see the
Yeah.
PowerPoint?
Very good. Very good. Very good. Very good.
What about now?
This challenge was kind of tricky. Yeah? Let's see how you guys did. Go ahead.
Okay, so we are group 1, and this is the challenge 2, exploring gradient descent and its variation for deep neural network training. And our goal in this challenge is, first, we need to build up a NumPy model in which we use the formula and calculate the forward passing and backward propagation ourselves. And then we need to build another PyTorch MLP-DNA model to compare with it. And the goal for both models is to identify the MNIST data sets. And then we need to calculate the real error in the PDF file, which means to check if our two models is the same. And then after this, we need to finish the dataset arrangement and training procedure. After that, we build a different optimizer, first order and second order. Then we can finally train our model with our different optimizer and see what's their outcome. And here's the code part. So first we build up two models. This one is the NumPy model. So we first randomly generates the weight and bias, and then we use the only formula to calculate like ReLU activation function and softmax activation function. And then this is the forward passing to pass the bias and weight to the next levels. And here is some small functions like get parameters, which used to equalize the NumPy and PyTorch parameters. And this is the get catches, which we use to let our optimizer to get the catches inside our model. And this is the set parameters, which used to set back the parameter to use in training. And here is the back propagation for the NumPy, and it's all the formulas in the PDF. And then here is the PyTorch models. So we can use the functions and math already built in to build up these models. So the command line are short. And here, the thing we need to focus here is that PyTorch built-in function will randomly generate weight and bias, not like our NumPy model. So in the comparison section, we need to first make them the same to compare. And here is the back propagation.
Right? You have to fix the randomness, yeah?
Yeah, and here is the back propagation for the PyTorch. So here we come to the gradient comparison. We first build the model layers, and then
oh wow! So you had how many layers did you have? You have 10 layers.
9 layers.
9 layers.
In the PDF, it says close to 3,000 neurons. So, and we choose like 3 and 4 different models. This one is better to find out the time and the loss.
Yeah, very good. Very good.
Okay, so here, here
so
we build out to.
Yeah, just to check. Let me just check a second. So do you have the NP seed and the torch seed? You fix them. Okay, go ahead.
Okay, so here we build the model, and here we compare the gradient. And then here is the training functions. It's a little bit small, but yeah, you can see just.
So the point is that you just do one step of SGD, right? So this your NP optimizer is just one step of SGD, right?
Yeah.
Because you have the gradients there, right? and then you evaluate. You don't have the line numbers, right? But basically, you have one step of SGD. You have the backward. So get cache gives you the forward activations. And your batch size
Yeah,
is 4.
here is just the training function, and later will be the optimizer. So here is just the training function to train both models. And here's the data set arrangement and visualizer. Visualizer is just to plot the outcomes of every training epoch. And the data set arrangement is just we get the data set and then we separate it into the training data set and validation data set.
Yeah, so you also normalize the data set and so on. So yeah,
Yeah.
usual stuff.
And here is the different optimizer in first order. So we have gradient descent normally and stochastic gradient descent and the momentum and the top K gradient descent. And this first two is easy, just as little formula to put in and then we can make it. And the momentum is a little bit longer. It takes the velocity to make sure that even the gradient change, but you still remember the velocity, so it goes to the direction it used to be. And the top K is just using the top K biggest gradient to change the model to let it study. And here's the optimizer in the second order. So we need to build the Hessian first, and here's the code to build the Hessian. And then we use the Hessian to create the Newton optimizer and diagonal Newton optimizers.
So where did you get the background material on the Hessian on the second order optimization? Was it easy to find? Did you guys have good references for the optimizer? Did it make sense to you? Tell me a little bit. Yeah.
It's not that easy, but we try to figure it out.
Does it make sense to you? Like, because usually you see the Hessian for scalar function, right? So, but this is a Hessian for multidimensional functions, right? So the Hessian is a matrix. Yeah. Did you? Yeah. Tell me a little bit. How was it? Yeah.
It's not that straightforward, and we need to think. And it's harder.
Okay. Very good.
Okay, so here comes the main part of our code. We just use 4 different optimizers in the first order, and then we just train it in different epoch, and then we compare both with the NumPy model and PyTorch model to see, even if we are using the same model, are they better if we write our model manually or use the original build-up functions. And then we also compare the loss function, how good for each different optimizer to let it fit. And then also the second order in the bottom part. So here's the observation part. We will introduce different optimizer and comparison of their outcomes. And this part, another group mate will say it.
Okay.
So can you see my slides?
Okay.
Okay, so I'll briefly introduce how all kinds of optimizers works, and then I'll introduce about our results. So first we have gradient descent. So in gradient descent, it look at every training example and calculates the exact gradient and move the weight a small step in the opposite direction. And this kind of a gradient descent is reliable but slow, and it scans the full data set, and the step size has to be tuned with care. So next we have the stochastic GD, which is the SGD, and it keeps the same update rules as gradient descent, but it uses a smaller mini batch to estimate the gradient, and each step is much cheaper and it has built-in randomness to help the optimizer avoid shallow minima or shallow traps. And next we have the momentum. So momentum adds a rounding average of recent gradient, which is called velocity, and it updates with the velocity, and that makes it smooth out the noise and builds speed along direction where the slope is consistent. And last, we have the top K. So it basically just get rid of, it basically just only save the K largest gradient and store the rest in a buffer. And the next step, the buffer is added back before we select the new top K. So information isn't lost. It's just delayed. Okay, so this is our training accuracy of our first order optimizers. And
yeah, wait a second. Let me soak it in a second. Because you have too many curves. So the tallest one, what is pi? Yeah, can you help us see the curves a little bit? First of all, yeah. So is this averaged or is this only one iteration?
既然你要讲嘛。
Okay, so this is the one iteration.
Okay. So next time, maybe in the final report, try to, I know it's very heavy, right? But try to average across, let's say, a few initialization, right? So that you can see what happens when you average. Okay, very good. So can you tell me the lines from the best one to the worst one, what they represent? Because the colors are a little bit messed up. So the tallest line is, yeah, go ahead.
Yeah, the tallest line is PyTorch SGD, and if I remember correctly, it's PyTorch GD. These two. And
we don't see your pointer. We don't see your pointer. Just tell me. So the first two should be PyTorch GD and NumPy GD, correct?
No, NumPy GD is in the middle. It's PyTorch GD and PyTorch SGD.
Okay, so because here what's the batch size?
Let me say something. The NumPy GD is the best in the NumPy set. It is the best, and then is it better than NumPy SGD and Momentum and Top K? However, PyTorch SGD is better than PyTorch GD. I think maybe it's just one iteration and not the average, so it might be some errors.
Yeah.
And our batch size is 64.
64. And when you do GD, you do over the whole 3000 MNIST dataset, or?
Yeah.
Okay, so should I move on?
Just a second. No,
okay, sure.
So the worst one is Top K, of course.
Both NumPy Top K and PyTorch Top K is the worst ones.
Okay, good.
Yeah.
And then Momentum, what is Momentum, guys? Are the pink and so the pink is there. What's the NumPy Momentum is the green one. Okay, good.
And by the way, if we choose not that accurate learning rate, the Momentum will be the best because it's have the velocity. But in this case, we choose the very suitable learning rate, so they look almost the same.
Got it. Very good. Yeah, go ahead, guys. Go ahead. So these are my two comments, right? So maybe next. So what you can also do sometimes is that you can log the accuracy. So the range between 0 and 1 get projected between 0 and plus infinity. So it's easier to see the difference between the curves. Otherwise, yeah, these two things. Repeat over multiple batches and try to log the accuracy to see if you can spread out the differences between the curves. Go ahead, please. Very nice.
Okay, so basically, Top K performed the worst at first, but the curve kind of like the performance is kind of very similar to one another after several epoch. And the next one, we have the training loss of our first order optimizer. And same here, 2 top K has the highest loss here at first, but then their performance is quite similar.
So
And then-
what is the loss here? BCE, what is it? Misclassification error, F1 score. What is the loss here? Guys?
I'll have to check the code because, or Dan, can you, because
which
yeah.
which optimizer is lost?
No, just in general, because before, can you go back to the previous slide?
Yeah, sure.
You see here in the accuracy, you see that the final values, right? They are still not converged to the same value, right? They go between 1 and 0.98. So if you can you go to the next loss? So I was wondering what you choose as a loss here, because then they converge all to the same value. So that's all my question.
Actually, it's not that same, but they are in the same 10 minus 2.
Yeah. I understand. It's just that I assume that the loss is going to be the BCE, right? And the accuracy, you're going to take, yeah. Okay, it doesn't matter. Go ahead, guys.
Okay, so here we have the test accuracy, and basically all kinds of optimizer perform very similarly, nice. And they all have ups and downs, but there's not a very clear trend of whether maybe which optimizer is better. There's not a clear trend of that.
Let me ask you something. So top K, what's the specification level of top K? 90%, 50%, what is it?
Let me see. 90%.
Okay, good. Yeah, very nice. And also here, we try to repeat this with multiple seats if you can. So you can also plot the variance, right? So you can also see the variance across multiple iterations. Yeah. Okay, very good. Go ahead, guys.
Okay, so next, I'm going to talk about the Newton's method and the diagonal Newtons. So that's the 2 second order optimizer that we did. And the Newton's method is rescales the gradients by the local curvature, and it aims for a direct path to the minimum value. So when the curvature estimate is accurate, the method is extremely fast. But when it is not, the updates can maybe overshoot or diverge. And next we have the diagonal Newton. So to make Newton practical, we only keep the diagonal of the Hessian. So that gives each weight its own adaptive learning rate based on how steep that dimension is, while staying computationally cheap.
Excellent.
Yeah. So this is the result of our training. So basically, the loss is very low, and it stayed very low. It kind of converged to very near 0.
Yeah. So yeah, also repeat this, please, so that we get some accuracy.
And
because
and the advantage of the second order is that it converges very fast, but it needs more calculation time. And here we can clearly show that it converges very fast at the first epoch.
Very good. Yeah, so because here you didn't see much difference, try to maybe log something, try to show the differences a little bit better, because yeah, you cannot see the difference between the 2 methods, right? Just in terms of representation. But yeah, go ahead, guys.
Yeah, so let's move on to the training accuracy. And similarly here, there's not much difference between these 2 optimizers. So is there anything you want to add, Jan?
Yeah, it's just like this. they did good job and they take long time, and that's it.
Okay, so let's move on to the last one, which is the test accuracy, which is still similar to the previous slides. Okay, so that is all for our presentation.
Very good. Very good. Good job, guys. Yeah. Just try to represent the differences a little bit better. I know that you guys were rushed for time since it's midterm week, but yeah, good job. But yeah, group 2, please go ahead while you prepare. Challenge 2, group 2. Challenge 2, group 2. Yeah, guys, try to stay around the 20 minutes with the presentation. I mean, it's very interesting stuff, right? So we're not getting bored, but just. Yeah, go ahead.
Okay. And we are group 2. And today only 2 of us is online because one of our team member never show up, and one went to see a doctor last hour. He is on his way back, so he will be online later. We will cover his part as we can.
Yeah, so for the one that remember, so if somebody doesn't work, remember to give them a 0 score. And then when we release the profile of the students at the end of the week, we will point out the people that didn't participate. So we discussed this already, guys, right? I know it's unsatisfactory. There's some people are free riders, but we have to move on with our life despite this. Please go ahead.
Okay. And this is the goal of our challenge is to first, we require to implement a fully function multi-layer perceptron or MLP using only NumPy. That means designing the forward and backward program completely by our hand based on the chain rule and the matrix calculus. Second, we explore both first-order optimization methods like gradient descent, stochastic gradient descent, and momentum, and second-order methods, including Newton-like techniques using finite difference approximations of the Hessian. Third, we implemented gradients diversification with error feedback, which allow us to simulate training under resource constraints like limited memory or communication bandwidth. And finally, a big part of the challenge was to visualize training dynamics, including how loss accuracy and gradient norms evolved, so we could directly compare how different optimization methods behave over time. All these components we are integrated into a single NumPy-based training pipeline, making this one of the most technically demanding, but also a challenge for us. Our process is to first use MLP and then backprop and optimization, and then we visualize it. And the other group member will talk about the data sheet.
Hi.
Hi.
Okay, so now I'm going to introduce the MINIS dataset. We use these datasets to predict to train the MLP model and try to predict the output.
Let me ask you a question. When do you think the dataset was released?
I think it's a very long time before.
Yeah, like in the 1980s, right? And you know why it was used, right? Can you guess what it was used for?
I believe just for the convolutional CNN model.
No, but like originally they wanted to use it for the recognizing the address of people, right? So when you write the mail, right, they had to recognize the digits of the mail, right? So for example, you know that there is the postal code, right? So when they were doing the sorting of the mail, they really wanted to be able to recognize the number of the postal code so that you could directly send it to the right person. So this is the original application was for mail. Go ahead.
I see. Okay. And this dataset consists of 60,000 training images and 10,000 test images. And each image is composed by 28 cross 28 pixels. And the model's goal is to predict the image and output a corresponding digit from 0 to 9 for each image. And we try to implement a multi-layer perceptron to complete this challenge. Our model consists of three layers, and the input layers is 784 inputs. This is because of 28 times 28, and it goes to a value activation function and a linear
Linear
layer.
layer.
So we have two hidden layers. One is 128 and one is 64. And finally, we have the output layer with 10 neurons. And after the softmax function, we have our prediction.
Mhm.
And this is the structure of our MLP. Now I'm going to talk about the first order methods, a gradient descent and stochastic gradient descent. The gradient descent is to use the learning rate and the training loss to update the weights. And the stochastic gradient descent can be regarded as a stochastic approximation of gradient descent because it only used a mini batch of training data. So it don't cost you a lot of time for training, and it doesn't use a lot of training resources. And this is the implementation of the gradient descent and stochastic gradient descent. The stochastic gradient descent, we use a mini batch to implement. And another first order method, we use the momentum.
Mhm.
The momentum helps us to accelerate the convergence and reduce oscillations by accumulating path gradient into the velocity vector.
Mhm. Mhm.
As it remembers the vector and uses to the next updates, I guess.
Mhm.
And this is our implementation. So
Can you go back one slide?
you try to remember the velocity and
Mhm.
use it to the next update, weight update. Yes.
No, I'm just checking if you like. You're gonna have another initializer, right? Because here the weights are set to 0. But it doesn't matter. Go ahead. Go ahead. Yeah.
Okay. And I guess I give it to another team member.
Where is the other team member? Here you go. We're back.
Okay.
And as our models grow in size, computing and storing full gradients for every parameter can become a major bottleneck, especially in the large scale or distributed training environments. So we use second order, and gradient sparsification is a technique that addresses this by retaining only the top K most significant gradients, that is, the ones with the largest absolute values, and setting the rest to 0. However, they introduces a problem. What if some important gradients are small but consistently present across many updates? Simply dropping them may slow convergence or hurt our model quality. That's where error feedback comes in. Sorry. Instead of discarding the dropped gradients completely, we accumulate them in a buffer and add them back in the next iteration. This way, small but consistent gradients still get updated over time without increasing the communication or memory overhead. We implemented this mechanism from scratch, including a buffer that keeps track of dropped gradients per parameter and updates it every step. This ensures convergence is preserved even under aggressive sparsification.
Just a second, what is Newton? Can you stay on this slide a second? What is Newton here? What do you mean Newton? You mean the
Newton?
second order? Yeah.
Second order Newton?
No. Next slide.
Next slide.
Slide 12. So here you see that in the top figure you have this Newton, right? What do you mean by Newton here? You mean the second order, the Hessian one?
Yeah.
So this one here, you calculated the Hessian as the previous group as a square matrix, or did you approximate it with two first order? Can you tell me how you implemented this?
About this chart, it was made by the teammate when to see a doctor. So maybe when he back, we will know.
I'll ask him.
Yeah, I just covered his picture.
No, because I just want to understand a little bit, because the fact that the sparse is close to the Newton method, it's kind of strange, right?
Yeah.
Because anyway, so we'll ask him. And then on the bottom you have the training time. No, what do you have on the bottom plot? So you have the norm. So what is the bottom plot? This is then the final accuracy. Can you tell me about the two bottom plots? One is the training time, and it's in the number of epochs, right?
Yeah.
And then the accuracy, because the accuracy is I don't understand, right? Because, for example, the momentum achieves an accuracy. Yeah, what's a bottom right figure supposed to say?
From my observation, their training time almost the same, but Newton and the sparse accuracy is a little bit lower.
Okay, understood. Yeah, because you choose the number of epochs that you train them for, right? So it's like if you do an epochs, if you see the number of epochs to reach a certain accuracy, then it will make sense. Otherwise, these are all 30 because you chose them to be 30, right? So not very informative. Go ahead.
Okay. And because we implemented our entire training pipeline manually, one crucial step was to verify that whether our gradients were correct. To do this, we built a PyTorch model with exactly the same architecture and initialized it with the same weights as our NumPy model. We then ran a forward and backward pass on the same mini batch of data and compared the gradients layer by layer, both weights and biases. The result was a relative error consistently below exponential three times for all layers, which is a strong indicator that our backward pass was implemented correctly. This verification process was essential. Without it, we would not be able to trust any of our training results or optimization comparisons, because we need to check whether we are on the right way. This
I mean,
verification.
if the accuracy goes down, then you're doing something right, right? So the accuracy is still good, but the test accuracy is another indicator. But yeah, I understand what you mean.
Yeah.
Go ahead.
This verification process was essential. Without it, sorry. It also gave us more confidence when debugging, because we could isolate whether a problem came from the optimization logic or from the gradient computations themselves.
Very good. Yeah, so this is what's gonna stay with you in the future, right? That if you're doing some learning, then you know how to go and check the gradient statistics to understand how is the training process going, right? So go ahead.
Okay. And the result, one of the most insightful parts of this project was visualize how different optimizers behave on the load surface. Yeah. And we can have lower computation and memory usage, or we have to wait for a long time and get the wrong results and waste a lot of time. So I think use this method can help us to compare our accuracy one by one to check whether our program is improving. Yeah. Okay. And I will give it to another teammate.
We're waiting for the other team. So next time, for example, if you want to switch order in which I call the groups because a student is doing something or cannot join a certain moment, just let me know before class, right? There is no problem.
Okay.
You don't have to go from group 1 to group 5, right?
But I believe the person is go to the hospital. That person are responsible for this slide.
For the part. He's not back yet.
Yeah, he's not back yet, I believe.
Yeah, just go ahead, guys. Just finish the presentation. It's okay.
Oh, okay. So we use the verification with PyTorch model, and we found that the relative error is less than 10th exponential of 3.
Yep.
Yes.
Good.
And
Oh, nice. Next plot. Let me see the next plot.
Yes, the next slide.
Very good. Just slowly here, right? Slowly here. So, why don't they start all at the same point, guys? Why don't they start at the same point? Because you fix the initialization, right? So that, yeah. Why don't they start all at the same point, guys?
I think the person go to the hospital can answer this problem. I believe it is because some initiative parameters, maybe.
Yeah, but that's what you can do, right? You can fix the randomness in PyTorch for reproducibility. And yeah, and you can, so because you have to fix all the randomness, right? So you have to fix the randomness in the initialization, the randomness in the mini batch, and then, so I understand that, for example, no, because at the beginning you're just evaluating, right? So yeah, anyway, so they should start all at the same point, guys. Okay, anyway, go ahead.
So next slide.
So the specification, do you know the specification level? Is it 90% specification?
Let me check about it.
The momentum should be like 0.7, 0.8, the beta parameter.
The correct percent is 10. It's 10.
Okay. Okay. Good. Okay, good.
Okay. This is the results.
Let's see if you have the test loss. Go ahead.
And the next slide.
Do you have the test loss, guys?
At first.
Yeah, because there was only the training loss, right? Do you have the test loss? This is training. Do you have test?
No, we haven't done it yet. Maybe
Yeah,
we
please
can,
do add test, right? So we can check test loss. Yeah.
Yes, we will add it to the final report.
And also try to have them start all at the same time if possible. Okay.
Okay.
Okay. Good, guys. Any other comment? Otherwise, we go. So missing test loss, missing random seed initialization.
Yeah.
Please
we
add
will-
it to the.
We'll complete that in the final report.
Very good, very good.
And take a
I know you
look.
guys were very busy this week, so. Okay, no more question for me. If there is some question from someone else, otherwise, group 3, please get ready.
Yes.
Okay, go ahead. If you're ready, group 3, go ahead.
Okay. And can everyone see it?
Yeah.
Okay. And we are group 3, and we're done in challenge 2. And here's our job distribution. All of our members have done things and
Very good.
and writing different code. Some doing model, some doing optimizer, some doing second order. Yeah.
Very good. I'm very happy to hear.
And first of all, we'll start it at the main point P1, which is an overall. The main PY is using NumPy to train 4 MLP training process, and then we'll do it at MNIST dataset. MNIST dataset using NumPy, and then it supports the first order, such as the SGD and momentum, and top K with error feedbacks, and also the second order, like the Newton-like optimization methods, and also you can collect the key diagonals, including loss, and including loss, accuracy, gradient norms, and Hessian-based diagonals. And at first, we'll start to set up the hyperparameters, and then we'll start to loading the data from the data point py, and it will load the MNIST data, and we'll try to normalize and reshape and doing one hot code of it. And then it's the model and backdrop initialization. You will start to build up an MLP, which is capped is below 3,000 neurons, and it's like this. And then next, we'll try to do the training loop and gradient norm collections. what it will do is to try to let me think. It will try to train data is shuffle and process in millions strings. And the MLP process each mini batch to produce predictions, and the cross entropy loss is contribute, and accuracy is measured by comparing predictions with ground truth, and the back propagation calculates gradients for each layers. And next one, we'll do the Hessian diagnostics and second order updates. It's because that when the use second order is true, then the training loop will use the Newton-like updates. And in this process, it will do the Hessian vector product with HVP. When the code is compute an approximate HVP using finite difference, the Hessian diagonal values, attributes values of HVP for each layer are accumulated. And then it will do the updates and analysis. And finally, it will show up the visualization, which includes 3 parts. One part is the metrics of the losses, which include training losses and testing losses, and the accuracy over epochs. And then it will have the gradient norms, and also the Hessian diagonals. Yep, it's an overall of main point P1. And next is model point P1.
Hello, everyone. Today I'll give a quick tour of our model.py file. This file builds a simple MLP from scratch using NumPy, setting up the network structure, initializing weights and bias, and getting everything ready for training. Oh yes, let's dive in. So, all right, move on to the initialization process. In the constructor of our MLP class, we pass in a list that defines the size of each layer. Based on this, the code sets up the whole structure. There are 2 main dictionaries here. One called params that stores all the weights and bias, and another called catch to temporarily keep track of intermediate value during processing. Notice that the weights are initialized with random value scaled by the heat initialization method to ensure stability, and all bias are simply set to 0. This setup is fundamental for ensuring our network starts on the right foot. Next page. Okay, now let's talk about the activate function and how the forward propagation works. Our class implements 2 critical types of activation functions, the ReLU and the softmax. First, the ReLU is a very simple function. It just returns the greater value between 0 and the input. Its derivative is also defined, which is essential for background propagation later on.
I'll stop you there, right? Is 18 the derivative of 15? Let me ask you.
Sorry.
So is the function in 18 the derivative of the function in 15?
The derivative of the ReLU function.
Yeah, someone else in the group knows where I'm going with this, right? Do you understand what I'm talking about? Do you understand my question?
No.
When you are in high school, I think, yeah, and you study the derivatives, right? They tell you
Yes.
that the derivative is defined for what type of functions? Not for all functions, right? Not all functions have a derivative, right?
Yes.
So in order for a function to have a derivative, they tell you that the function must be anybody? Must be continuous, right? So it must be continuous. Correct? Which means that the limit from the left to the limit from the right for each point of the function must be the same. Good. So, but the ReLU has a problem, right? The ReLU has a discontinuity, right?
Yes. Yes.
Okay, what type of discontinuity is? You remember the types of discontinuities? It doesn't matter, right? But you do understand that at the point x equal to 0, the function is not continuous. Do you agree?
Yes.
Okay, so the derivative in 0 doesn't exist, right? Because from the left, the derivative is equal to 0, and from the right, the derivative is equal to -1. So it doesn't exist. So what you do you agree with this? Do you agree?
Yes.
So you understand, right? So from the left-hand side, the derivative will be -1, and from the plus side, it will be equal to 1. So what you do is that at the point equal to 0, you don't have a definition of derivative, but basically you just go on regardless. Right? You ignore this issue and you use it anyway. And the idea is that any slope of the function, right, will work at the point is 0. So yeah. So anyway, so the definition in IS18 is what you would call a subderivative, right, or a generalized derivative of the ReLU, meaning like the ReLU is not continuous, so you have to change the definition of derivative, and 18 is a subderivative. Go ahead. You understand my point, though, right? You understand my point?
Yes.
Okay, go ahead.
Okay, so next is for propagation. In the for method, the input data is first transposed, so it matches the expected shape. Then for each layer, the method calculates the linear combination with weights and bias, applies ReLU, and stores the immediate value in a cache. So finally, the output layer applies softmax, yielding probabilities for each classes, and the method returns the result with the proper shape. This process forms the core of how our model makes prediction. Next page. Okay, finally, let's cover how our model evaluates its performance and manages its parameters. The compute loss method calculates the cross entropy loss, which is a standard measure to see how well our model's predictions match the actual labels. It even adds a small number to avoid issue with taking the logarithm of 0, which is a neat little trick. Next page. So we also have two utility methods.
Can you go back? Can you go back one slide? Can you go back one slide? You are missing something here, right? In the loss, you don't have the true label. You see, in the loss, you should have the true label. You see, in the loss, you only have the y hat, but you don't have the y. So you're missing the true label in the definition of the function, because this function is you see, you understand? Okay. You see that you have prediction and labels, right? You see that the labels give you the anyway, fix the equation. You understand the issue, right?
Yes.
Yeah, go ahead. You're missing
Okay.
an indicator function. Should be indicator function of y equal to. Yeah, go ahead.
I'll fix it. Okay. Yes, we have two utility methods. One is get parameters and set parameters. These two methods let us retrieve and update our models, weights, and bias easily, which is very useful for further experiments. And yeah, that's it. Next page.
Okay.
Hi.
Hi.
Okay. So now I'm going to talk about the part of optimizers. And it includes the first order optimizers and the gradient specification. Next page. So first is the GD. So look at the up left part. We set the learning rate to be 0.01. And the formula is on the left down part. Yeah. So here's so look at the up right part. So here's the graph of test loss and the test accuracy.
Yeah,
so
good.
You can see that the accuracy is quite high. And also we also show the graph of the gradient norms of each layer. So it decreases. So each layer is decreased. So it means that it's converged. So it makes sense for us.
Just a second, let me think. So here, okay, sorry.
Okay.
Got it. Just a second. So here, this is GD. So you did a whole 60,000 samples, right?
I should ask the other teammates to ask about, because I just call the function and do the
Something happens.
Yeah,
No, I mean, I hope you didn't do all the 60,000 samples, but yeah, something like that, right? Like a very large.
Okay. Yes.
And then so the weights. So then let me see the gradient norm, right?
Yeah.
So because you have that the gradient norm in the bottom layer is 0.6, then it goes to 0.7, then it goes to 1. So here, are you counting the layers from the bottom to the top or from the top to the bottom? Top to the bottom, right?
What do you mean? So count this.
Softmax is here, right? Input is here.
Yeah.
So is layer one the one closer to the input or the one closer to the output?
So layer one is more neurons, closer to the input.
Closer to the input.
Yeah.
And the norm, is it normalized by the size of the gradient? Must be, right? Do you normalize the norm by the size of the gradient?
Yeah, I think, yeah.
Because
the gradient is calculated by other codes. So I just call the gradient and do the algorithm.
No, but when you plot it, you don't normalize it, right? So you know what I mean? You don't take sum of the square divided by the size of the norm, right?
Yeah. So I didn't normalize it when I calculate the GD.
Okay.
But
because
it before. Yeah.
Because you understand what I ask you, right? Because usually, right, the gradient norms, they are larger, closer to the output, and then they get smaller as they get closer to the input. Because basically, when you do gradient descent, you either have that the gradient is vanishing or you have that the gradient is exploding. You're always in these two, right? So that's why when I see this picture, the gradient increases as you go up. So I don't know if it's because, you know what I mean? It's just strange to me because I would expect that the gradient decreases as you go up. So my suspicion is that if you normalize the gradient by the size of the layer, then you will see that the gradient is decreasing. The gradient is decreasing as you go up. That was my question.
Because the algorithm of making this graph is other team to make the visualizer. So yeah.
No, but again, so I'm not here to criticize. I'm not here to criticize you. I just want to understand if what I see is what I expect, right?
Okay. So next page. And
Yeah, and then I also like that here you see the crossing between trust and train accuracy, and that's around epoch 10. Okay, good.
and
Try to clarify this part in the final report, please. Go ahead.
okay. So next page is the actual data to make the graph of the test loss and the test accuracy. So you may see that the test accuracy of the first approach is 89.8%, and the last approach is the 96.9%. Yeah, so it's a high number. Yeah, and we will see that to compare to other optimizer. Yeah, next page. So next is the SGD. So here we choose the mini batch number to be 64. And so we could see that the curve of the test loss and the accuracy is similar to the GD, but the intersection of the two lines in the test accuracy is around 10 approach, and in GD is around 7 to 8 approach. So it means the speed of the convergence becomes slower, and the gradient norms are higher than the GD.
Yeah.
Also, we can see that. Yeah. Next page. So here's the actual data. So we can see that the last approach only have 95.4% of accuracy. So it's slightly slower than GD, but it's also a good result.
Good.
So first is the momentum. So we set the momentum beta to 0.9 here, and it's still a good curve, and we can see that the intersection of the two lines in test accuracy is around 7 to 8 approach, which is similar to GD. Yeah, so it's also a good result. Yeah, next page. So here is the actual data of test accuracy. So at first, we can see that the accuracy at the first approach is higher than SGD, and is similar to GD. And the last approach is slightly lower than GD. So for the momentum optimizer. Okay, next page. So next is the gradient specification. So here we set the top K ratio to 0.1, which means that we use 0.1 of the total neuron to make top K. Yeah. And we can see that the intersection of the test accuracy is around 7 to 8 approach. And we use these methods to act as a first order optimization. Yeah. So compared to 4 optimizers, so only the SGD have a lower effect. So the other 3 optimizers are similar in this case. So now we are talk about the next part. Okay, for next email.
So as for the other group, so if you can have a plot where you maybe do the averaging over multiple initialization, I think it'd be nice.
Yeah, but I tried a few times when I was just before the presentation. So the result is similar, but it takes much of time for data analysis. So
of course, because everything is done in MP, right? So you don't have any GPU. I mean, of course, it takes a long time.
So I just make everything to make sense for me. Yeah.
Very good, very good. Okay, go ahead, guys.
Okay. I'm going to walk you through a practical implementation of Bayesian approximations and how we can use them to perform Newton-like updates in neural network training. And we'll look at how second-order derivatives can enhance learning efficiency using a simple yet effective approach. So, okay, first-order methods like gradient descent work well, but they ignore a curvature of the loss landscape. And second-order methods use Bayesian or second derivatives, which can lead to faster and more stable convergence. But the for Bayesian is huge and expensive to compute. So we approximate the product of Hessian with a vector instead.
Okay.
Next. So the Hessian approximation class is designed to be a wrapper around any model object with forward, loss, and parameter method. It approximates HVPs using finite differences and then applies Newton-like updates using those approximations. And what we can see on slide is our our major function. Okay, next page. So for the finite difference HVP method, this method loops through all layers in the model. For each weight and bias, it perturbs the parameter slightly in the direction of the gradient and compute the change in loss. And this let us estimate the Hessian vector product using the symmetric difference quotient.
Very good. Very good.
So the result on the right-hand side of the slide, the result is a dictionary of approximated HVPs for each parameter. After computing each perturbation, the original parameter value are restored to avoid drift. And this process is repeated layer by layer for both weight and biases. Next page. Okay, the helper method computes the loss for the given input. It's essential to use the same forward and loss logic as the rest of your my training code for consistency. So for now, it's called dummy. It's dummy, but in practice it should be an actual training loss. And next page. So once we have the HVPs, we can use them to scale the gradient update. This resembles Newton's method, but we add a damping term lambda to avoid division by 0 or small values. We also clip update to prevent instability for large jumps.
Correct.
Next page.
Correct.
So to use this class, the model needs a consistent interface. It should expose its parameter as a dictionary and support getting and setting them. And also it must implement forward and loss method. And this setup makes the class compatible with most custom neural nets. Okay, and the next teammate will talk about a visualizer.
Okay, I'll talk about visualizer. And visualizer is to try to graph all the stuff, which includes the plot training and the plot training and testing loss and accuracy curves over epoch, and also try to visualize the evolution of gradient L2 norms across layers. Critical for understanding the impact of the top K gradient sparsification. And also include additional diagonals such as the Hessian spectra, or called Hessian diagnostics, if computed, which provides insights to the curvature properties of the models. So the first one is the loss and accuracy curves. So it's to train the train and testing loss and accuracy over epochs, and it allows easy comparison of models' performance across different optimization methods.
So this is this curve here is for GD. What is this curve?
this curves it can I think this one is SGD.
Okay.
probably.
Good.
Yeah.
Go ahead.
You could just change it.
No, I understand.
And next one is gradient norm trends, that it can plot every layers, it can plot the L2 norms of the gradients for weight and bias of each
Mhm.
layers throughout the training process.
Mhm,
Yeah.
mhm.
And it could analyze the top K impacts to the gradients normal chains.
Mhm.
And next one is the next one is the Hessian diagnostic visualization, which is required for the step 6 of this challenge. It tries to plot out the additional Hessian diagnose data.
Yeah, so it's like an acceleration, right?
Yes, right.
Interesting
And-
that the first layer is going up, right? This is again GD, right? This is again SGD. Interesting. Oh. Okay, go ahead.
Yeah. And the next people will try to talk about the analysis about different layers.
Okay, it's me again. Okay, I'm going to talk about the result and analysis of Haitian part, the second order part. So for layer 1, we see that the Haitian spectrum for weight stays relatively stable, hovering around 1.5, and they suggest that layer maintains strong curvature, meaning the optimizers remain sensitive to weight update. Bias curvature is nearly flat, indicating minimal influence on loss landscape curvature.
Yeah, so because the bias here, even if you remove the bias, the network will do fine, right? Because MNIST is linearly separable, right? So basically, yeah. So you can also remove the bias basically from this network, and it'll work just fine. Yeah, go ahead.
Okay, thank you. Next page. So for layer 2, we observe a gradual decline in the weight Haitian value from 0.6 to about 0.18. This suggests that as learning progresses, the model becomes less sensitive to parameter changes in this layer. And bias again show almost no curvature. Okay, next page. Okay, so for the last layer, which is layer 3, displays a pronounced drop in curvature, with Haitian values shrinking rapidly from 0.4 to nearly 0. This may imply that deeper layers reach flatter regions of the loss surface more quickly. Again, the bias have almost no curvature impact.
Correct.
Okay, next page. So from this visualization, we can see that early layers maintain higher curvature, potentially requiring more cautious update, and later layers flattened out, indicating more stable convergence. Since biases have minimal curvature, they might be less critical in Newton-based update. Okay, next page. So for the summary of the result, Haitian diagnostics offer valuable insight into how different parts of the network respond to optimization, and this understanding can guide improvement in training strategies such as adaptive step size or layer-specific regulation. Okay. Next page. Okay, while this method is to conclude about the Haitian method, while this method is conceptually simple, it requires 2 extra loss evaluations per parameter group, which can be slow, and also the dummy loss might not perfectly reflect the true training objective. So in future versions, we might able to use autograd AutoGrad tools to for faster and more accurate HVP computation. Next. So in conclusion, incorporating second-order information like Hessian factor products can significantly improve optimization. Even with simple finite difference method, we can approximate curvature and apply Newton-like update to accelerate learning and enhance model stability. Okay, next page. Okay, thank you for listening.
So question. So the top K specification, do you have a figure with the convergence using top K specification? I didn't see it, right?
We so far we haven't used that.
And also for the second moment, you just use it to analyze the curvature. You don't have an optimizer that uses the second moment, right?
Yes, we just use the optimizer the same with the first order. We didn't write another.
Okay. Yeah, because those two were the aspect, right? To see the role of you didn't like basically the half of the challenge was more than half of the challenge was to use top K and the hash and the second order optimizer, right? So you just had one optimizer in the project. That's my point.
Yeah, basically we didn't try a lot of we did write different optimizer, but we did not use different optimizer. We did not apply those different optimizer to the second order derivatives.
But you have them. You have them implemented in the code.
Yeah, I remember that I have implemented, but I'm not sure whether it show up in the final result because I have comment out some code in the main function in order to reduce the running time, but I'm not sure that the one who do the final editing of the code has uncomment those code or not.
And then these curves here, you obtain it with MP, right? You have your MP implementation of. Sorry, you have the MP implementation of the network, right?
Yes.
Yeah. So basically, like you went into this Hessian curve diagnostic, which was not in the project, right? And you didn't implement the optimizers using top K and the second order method, right? So try to see if you can fix it by the end, by the final report, okay?
Okay, I see.
Because you guys went off topic. I don't know why you went off topic this week. I thought it was pretty clear. Okay, very good, guys. Let's take a 10 minutes break. I'll see you back at 55, right? 55. And then we go with the last two groups, okay? Take a break, walk around. We'll see you soon. Ciao.
Is teacher here? Is teacher here?
Yes, yes, yes. Tell me, tell me.
We're group 3, and we have something need to tell the teacher that.
Yeah. 哎，等一下我讲话，我等一下。
Go ahead.
Okay. And I'll
Yeah,
show.
we have something to clarify. Yeah.
Yes. Yes. That's we have done the top K and also second order optimization, and the only thing, and here's our code that we only need to change the comment here that change the optimizer to probably GD, momentum, and on top K. Yes. Just need to change those, and it will change it to the corresponding optimization.
Yeah. I mean, I didn't fix it by the final report and put everything in the final report, and it's fine, right? So, no problem. We'll adjust the grades when we see the final report. No problem.
Yeah, this is our implementation detail here. Yeah, so yeah, because it is comment out, so I thought that someone might delete it, but it's actually not, because I'm responsible for first version of the main function. So yeah, I'm.
Yeah, you see my just in the presentation I didn't see it, right? So that's my point. Yeah, but we'll fix it. Don't worry. Don't worry. You just put it in the final report and I update the grade. Okay.
Okay.
Good.
Okay. Thank you.
No worries. No worries. Okay, let me go get my drink while group 4 gets ready, please. Go. Group 4, are you guys here?
Hi.
Hi.
Hi, please wait a minute.
There's no sugar in the tea.
Could you see my slides?
Yeah.
Okay, hi everyone. We're group 4. And we'll walk through those steps and briefly introduce what we have done on those tasks. First of all, we have trained our NumPy model and plot those curves. And we first encountered the issue of overfitting, and after we modify our code and split our dataset into mini batches, the issue is fixed. Our batch size is 8, and we use SGD as the optimizer. Our epoch number is 80, and we use softmax and sigmoid as activation functions.
Oh, you use sigmoid as an activation function, okay?
Yes, we use sigmoid.
Sigmoid activation plus. So you use sigmoid from layer to layer? No. What's the deep layers? What's the activation for the deep layers? What did you use?
For the hidden layer and the input layer, we use sigmoid functions, but for the final layer, we use the softmax.
Softmax, yeah, softmax.
Okay,
so go ahead.
Next, we train our PyTorch model. Based on the same logic, we use the same settings, except that we alter our optimization. We alter our optimizer to Atom to enhance the convergence rate.
But you also have some learning rate scheduling, right? What's going on here?
Some learning rate, yes, some learning rate scheduling, yes.
Yeah, but the point was to check that the output of PyTorch was the same output of the NP, right? So did you check? Did you do the comparison? Okay, let's see. My point is that in the MP you didn't have the learning rate scheduling, right? And you only had 8 epochs. Okay, we'll see. Go ahead, guys. Let's see what happens.
Okay, then this is the heat map of the relative error values we calculated. We can see.
Sorry. So this is the relative error between the MP and the PyTorch?
Yes, between the two versions of models.
But you have so you have a 30% error?
In the middle of the training stages, yes.
Yes, so there is something. So it's not there is something wrong, right? So the
Yes, and we have focused on those on reasonable values, and we think we infer that this is due to the learning rate mismatches you previously mentioned.
Okay.
Because the after method use the adaptive mechanism to adjust the learning rate dynamically, so we should maybe use the same mechanism on our NumPy model.
Of course.
Okay, then for next page, the next email will introduce the following content.
投影片不用关，直接放就好。
哦，好 ，OK。
Okay, I'm the one in charge of step 3 and step 6, so I combined them together just to see here. Here are some the plus of the testing loss comparison and accuracy comparison during the training epochs. For each epoch, I will conduct a simple testing with testing data and training data both.
Just a question. What is M training here? The momentum?
Yeah, SGD with momentum. And the red line SGD is normal SGD without momentum. So as we can see, SGD is too unstable for application unless some momentum is added.
Question. So the SGD is you implemented with MP, right?
SGD with PyTorch. Just to enhance the training and coding efficiency, I conduct the 12 tests on PyTorch with my own CNN.
Yeah, because I mean here the SGD is not converging, right? I mean, it's just very strange. Like the training dynamics are completely different, right? SGD. What's a batch size for SGD? Also, the batch size, is it the same batch size?
Same batch size of 100 photos.
And there is this big difference between SGD and Adam. It's a little bit fishy. Okay, anyway, go ahead. Let's see.
And the same learning rate, but I set the learning rate higher, so this would be more dangerous for the SGD. But you can see it's converging, but very slow.
Okay.
I designed the parameters for Adam, so this may not be so suitable for SGD under the same settings. Okay, next page.
I'm the one who is in charge of the step 4, and first order is using the gradient descent, and we use the outer product approximation for the Hessian function for the second order optimization. Next page. And this is the differences between first order and second order. I think that the second order is convergence more fast than the first order, but when the epochs are enough, their accuracy will be the same. And this is the formula for the second order approximation. We add damping variables for it to prevent it from diverging. Okay.
From exploding. Yeah.
Next page. And this is the code. I made some changes in the update parameter function. And here we can see the formula from the previous page. Okay, the next page. And this is the result. we can see that when the epochs is enough, their accuracy is almost the same, and the second order is much fast to converge.
Did you check that this is consistent with the PyTorch evaluations to check that the code is correct?
Oh, no, I don't check.
Maybe you should have checked.
Okay.
Go ahead.
And this page, okay.
Okay, so for the final part, I will introduce the section about gradient specification. Here we include this mechanism and discuss our experiments through these three cases. We set the top K value separately from 10 to 100 to 1000, and it can be observed that the convergence speed for the second case is higher than the other two cases.
Question. So this is
Yes.
is that a percentage or is it an absolute value? So there is a 10%. Yeah. Which percentage is this? Like when it's 100, what is it? Is it 10%? Is it 50%? Is it 1%? What's the total number of parameters?
Total number parameters of the model.
Yeah, of course.
Think it's about. I have measured it once, and I think it's amount of 1,500 to 2,000.
So this is a 5% specification. A 2% specification. So go back to 10. Go back to one slide.
Okay.
So here you achieve 85% accuracy with 10 out of 2,000. Let's see the next slide. And here you achieve 100. So, okay, good. Let's see 1,000. Okay, good. So, but here, how did you do this? Did you have your? This is the implementation using Adam, right? Which optimizer are you using here?
I use Adam here.
So you use PyTorch Adam. You extract the gradient, you specify, and you write the update, correct?
Yes.
Okay.
Okay. So
because here there is some learning rate scheduling that is also interfering with things. Okay, go ahead.
Okay, so this is a part of gradient specification, and we also discovered that batch size also impacts the performance of convergence. We once set the number to higher values, like values above 100, and we encountered OON error, which stands for out of memory. And this means the GPU we use cannot store more data than we expected. And when we set the value too small, the performance is getting worse because the mean and the standard variance values are calculated in batch normalization processes are not incorrect because the lack of samples in many batches. Yeah, so top K values matter, and also batch size matters. So this is the end of our sharing. Thank you for
listening. That's it. That was very fast, guys. Okay, very good. Let's see the last group 5.
Hi, can you hear?
Yep.
Okay, wait for me. Wait for me. Okay, can you see that?
Yeah.
Okay, hi everyone, we are group 5. Today we are going to show our project. Firstly, we want to introduce the purpose of this experiment. In our previous challenge, we have learned how to use PyTorch package to build a DNA model. However, in this challenge, we will only use NumPy to build a fully connected neural network model. And it means that we didn't use PyTorch package in this challenge, except for we use in step 2 for gradient verification. And we use MNIST to do simple classification. And in this case, we need to use cross entropy and softmax function, which often apply in image recognition. Besides, we also use first order optimizer and TopK algorithm without using PyTorch package. Our purpose is to have a more impressive understanding in this algorithm, and that's why we code in manually.
Okay.
So let's look how we verify the manual.
Just you're not sharing the presentation window, right? We are still seeing slide 1.
Oh, sorry. Can you see that now?
Yeah.
Okay.
But
so,
you can also share the presentation window, up to you. Yeah.
Okay. So let's look how we verify the manual gradient with NumPy. So because we need to make sure our manual gradient is in accordance with the PyTorch gradient, we use PyTorch autograd function to make sure our manual model is on the right track. So, but unfortunately, we have a lot of fail in this step. We use a round loss function. It's a critical problem. We use NSE as loss function, and we didn't use softmax in initial. But finally, we solved this problem, and our experiment result is 3.46909 and 10 to the power of -8, and which is the expected number.
Very good.
So it seems that our experiment is successful, but we still need to explore some difficulty we met in this step. The first problem is that the shape of the manual gradient and PyTorch gradient are different. What does that mean? It means that manual gradient is 65 and 33, which is include the bias term. And however, in PyTorch model, the shape is 32 and 64. It didn't include bias term, and it will calculate its calculation is include bias, but the gradient vector didn't include the bias term. So we need to deal with some detail here, and which cost me a lot of time. And besides, we also need to use transpose to the manual model after we finish first backward calculation. So after finishing this these several steps, we can really make sure our gradient calculation is correct or not. Okay, so this is our experiment result.
Yep. Just a second. Stay on this slide a second. Manual autograd norm. Very good. Very good. Gradient summary. Okay. Good. Okay. Go ahead. Very good. How many hours did you spend to do this? Like 10 hours?
Yeah, for 5 days and 10 hours. Because there's a lot of errors. For the first problem is the NSE problem. I didn't realize that NSE need to be revised into.
No, that one that was your fault, right? Of course, if you choose the loss function, you have a different derivative. Yeah.
Yeah, but it still cost me a lot of time because I didn't know this thing. And besides, I didn't use softmax. Anyway, I missed a lot of information, and I didn't know where we should use this.
Very good.
And
in fact, if you notice in this today, you can really tell the people that they went through the exercise of making the NPy output equal to to the PyTorch output and the people that didn't, right? I mean, I think there is a lot that you guys learned from this exercise. Yeah. Go ahead.
Yeah. Okay, so this is the second time we use verification, and it's also the 10 to the power of -7. So the expected number. Yeah,
Question. When you do the norm, right? You take one gradient minus the other gradient, and you do the norm, correct?
Yeah.
Okay, good. Go ahead.
Okay, so after finishing this step, we can really explore the first order method like SGD and momentum. And in GD method, the model uses a full batch, which means that we update our weight without with a full batch with a full data set. However, in SGD case, we didn't use a full batch. That will improve some calculation speed, but however, it will also sacrifice some precision. So GD case will change more slower, but because we use a full batch, it will be more accurate. This page is Lin Mengxi.
Yeah, let me soak in. Let me soak this in. Yeah? Let me soak this in. Is this averaged? No, this is just one in the one. It's not average, right? This is across batches. Sorry.
Yeah.
This is the no. Stay here a second. I want to see the slide. Guys, bring me back to this slide. Bring me back to this slide.
This slide is planned for different batch size, and this is SGD case, but in this slide is GD.
Yeah, just stay there a second. Stay there a second. So the grade E, so that's the of course. Yeah, good.
Okay, so
is this average? It's just one iteration, right? This is not averaged.
Yeah.
It is not average, correct?
Yeah.
Okay. So basically, you're saying that if as you double the batch size, then you should double the convergence, right? But why is the initial loss larger with the larger batch? Can you explain to me? There's something fishy here, right? There's something fishy.
Hi. Sorry, my microphone went down.
No problem. So, can you explain this to me, because there's something weird with this plot, right?
Okay, so this is the curve of different batch size, and with smaller batch size, we typically get better loss curve and better accuracy.
But it doesn't make sense, though, right? It doesn't make sense. Does it make sense to you? You use the larger batch to calculate the gradient, so you get a better gradient approximation. So why would you have a worse loss? Are you sure?
I'm not. I don't know, but I think maybe this is because the MNIST is a easy data set. So
there are two options, right? There are two options. One is that you don't normalize the loss, right? Because did you normalize the loss by the batch size?
Yes, I did.
Oh, damn it. So why is the largest batch size giving you a larger loss? It doesn't make sense, right? Look, the batch 128 after 20 epochs gives you a higher loss than the batch 1 after 1 epoch. How is it possible? You do agree that there is something wrong, right? You must agree.
I'm not sure why, but I think we have done normal. We have divided by batch size, and
yeah, try to figure it out, because you do agree with me that there is something wrong, right? You do agree with me.
But I think maybe it's because with small batch, you actually train. You actually update more times in one epoch. Does that make sense too?
Repeat that. So what do you do? Come again.
With smaller batch size, you actually update more times in one.
But then how do you compare across? How do you make an epoch with one batch size equal to an epoch with 128 batch size?
Also, yeah. So with one batch size, it actually updates 128 times more than.
Okay.
batch
So
size
I see. So I understand. So what you're doing here is that in one epoch you are processing the same amount of data, right? I see.
Yes.
I see. Because that's not what I was expecting, right? I was expecting that. I was expecting that you calculate the gradients and then you do a number of. Understood. Okay. Okay. So actually, so the processing data. I see. So did you? So this is still implemented with MP, right?
You say this is with MLP?
NP,
Yes.
NP, NumPy, right?
NumPy, yes.
Okay, good. So basically what you're doing here is that you're throwing away any possible parallelization of your calculations.
Yes.
And then you update your model after each sample, right?
Yes.
And you say that if I do this, okay, now I believe you. Okay, okay, I believe you.
But batch size 1 is less stable than batch size 4. So
of course,
maybe size 4 or size 8 is the best choice. And the smallest batch size is beneficial when we're trying to escape local minima or when faster convergence is desired. But the downside is that it's more computation.
Of course, right? Imagine because you throw away all the, let's say, all the scaling by, let's say, matrix vector multiplication, right? Now, of course, the computational complexity is much larger, and also you don't, Anyway, that's nice. It's nice job, You confused me at first, and then I was happy that you explained to me. Go ahead.
Okay, next slide. So in the momentum method, the updates takes into account not only the current gradient, but also the past gradient. So this reduces sensitivity to high frequency noise on the lost surface. And this also helps escape local minima or flat region too. And particularly in directions with high curvature. So down here, these two plots are generated from the wave cycle why momentum really works. And these two have the same learning rate, but the left one has 0 momentum and the right one has 0.8 momentum. And as we can see, the momentum really makes the step more smoother. And when no momentum, your steps are very unstable. So momentum really stabilize your steps and help you converge. Yes. Next slide. And this is our training loss curve and test accuracy curve. So the gradient descent one is the worst, and momentum is the best. And
what's the batch size here? What's the batch size?
Gradient descent has 64, and the stochastic gradient descent is 4.
Okay, and the momentum is also 4. Got it.
No, momentum is 64.
Momentum is also 64.
Yes.
Okay.
Next slide. So in second order approximation, we try to compare it with first order, but we think it's not practical for most deep learning models. And this is because second order optimization is sensitive to curvature errors and can misdirect updates near saddle points like the plot on the left or non-convex regions, the plot on the right, the most right. Yeah, next slide. So ideally, second order optimization takes in curvature information and output a direction that potentially points more directly toward the minimum. So as the plot suggests, the green arrow is the inverse Hessian dot gradient, and it actually points to this is a very simplified case, so it actually points to the real minimum.
Yeah, because this is a quadratic function of some sort, right? So this is a quadratic function. So the solution should be the Hessian. Yeah.
Yes. Next up. And this is our training. Diagonal one can only performs under a specific training configuration, like layers or learning rate. Yeah, but other case, if it fails, and finite difference is never works. Okay. And
so you implemented this, right? You implemented this in NumPy, right?
Yeah, and we don't know why it never works. So, okay. So the outer product.
Go ahead.
The outer product can work, but it didn't really go to the less loss. The loss didn't decrease. It just goes.
Can you tell me why your starting accuracy is so high? Is 94 of your outer product after 5 epochs? I mean, that's right.
I'm guessing that since they are all initialized the same way, the same weights, so I'm guessing.
So you don't pre-train the model, right? The model is not pre-trained, right?
Yeah.
Because here it seems that you already achieved the best accuracy after 10 epochs, and after 10 epochs, of course, you diverge, but that's okay, right? I mean, your best test accuracy is still 95%, right? Because the other two models, they don't even get close, right? So
yeah, they are not pre-trained. So
question for you.
Okay.
When you do the finite difference, right, you have to choose and sort of a vector v by which you perturb your current gradient in order to have the finite difference approximation, correct? How did you choose that vector?
I choose it to be gradient L.
So you move along the gradient plus and minus a certain epsilon, right?
Yes, I
did. Because I think that implementation seems just wrong, right? Because basically you see that you stay around random, right? So you see that you stay around 10%, which is the is the error rate that you expect if you guess randomly, right? Correct?
Can you repeat?
So because the test accuracy, right, is the error rate, and you have 10 classes, so your error rate is going to be 1/10 if you guess randomly, correct?
Correct.
So you're just moving randomly in the parameter space. So basically, you're not doing anything, right?
Yeah.
So it seems that there is no just random, just moving randomly, basically. So I think there is some error in the code.
Yeah.
In the information.
My finite difference never works.
Yeah, it's very difficult to make it work, basically. Yeah. Because you have to decide these 2 points for the approximation, right? So you have to decide these 2 epsilon, and it's a very tricky problem. Yeah. Okay, go ahead.
Okay, next slide. And so gradient specification can alleviate communication and memory bottlenecks. So error feedback can compensate for a gradient when removed from last epoch, preserving the impact which brought from small gradients. But in a momentum method, since the velocity term depends on the previous update, the residual vector may not be able to fully compensate for the gradient error from the last iteration. Sorry, I think we didn't use the newest slide, so can I switch?
Of course.
Okay.
Yes, You think I don't let you switch slides? I'm so strict. There is no, you cannot switch slides, of course.
Okay.
There was a nice slide. Yeah, go to 15. Go to 15. Let me say 15.
Is the
Yeah, it's not updating, so you have to this one here. Stop. Let me see. So here you have so this is 90% specification. Yeah.
okay? So
Let me just absorb it a second. So GD. Very good. Very good. And very good. So GD, you do top K, you lose a constant like 0.2, right? If you do it with momentum, then you do lose again more, like 0. And then if you do, can you tell me where is the error feedback? The error feedback brings you back to the original curve, basically, correct?
oh yeah.
Okay, good. Okay, go ahead. Yeah, very good. That's a very nice plot. Yeah, go ahead.
So the top K version is very higher than original one. This makes sense because the parameters are not updating toward the direction of steepest loss descent. Okay. And this slide shows that top K and plus error feedback produce almost the same result as the original one without top
Incredible,
K.
huh?
And
Incredible,
this
right? You agree? It's pretty incredible, no?
What did you say?
It's pretty incredible.
Oh, yeah.
No, isn't that incredible?
Thank you.
No, I mean, if you had invented error feedback, then I will say that you are incredible. But you know, the guy, the error. Okay. Okay. I'm sure that you're incredible in your own way. Okay. I'm sure that you're an incredible person. Okay. I just meant to say that when you see this result, it is pretty incredible that you reduce the communication rate to 10% and you still do this. Again, I'm sure you're incredible. Okay. Good.
Thank you. Thank
Go
you.
ahead.
Okay.
Go ahead.
So this is because the discarded gradients are added back in subsequent updates. So
Thank you.
correcting for the specification. And from the loss and accuracy, we can conclude that it's almost at the same point in the parameter space.
Mhm.
That's why they have so similar loss and accuracy.
Mhm.
So, and the only source of divergence comes from the gradient difference of different coordinates updated by top K and no top K.
Mhm. Of course.
And so error feedback cannot fully compensate for specification in momentum-based optimizer, because momentum-based optimizer include the scaled accumulation of past gradients. So adding back the residual is not equivalent to the original gradient updates. So on the plot, you can see that other two methods, they are almost they are almost on the no top K one, but momentum based one, these three are separate.
Yeah, so in fact, this is what you're saying now. It's a direction of research that we also investigated, because basically there is, if you could come out with something which is Adam with error feedback, that would be a new RIPS paper. You know, it would be a very interesting paper because nobody figured out how to do this. Yeah? Because, for example, you can show that convergence with error feedback is the same rate of convergence as without error feedback. But you cannot do this with some variance reduction methods such as Adam. Yeah, so it's true. It's an active research direction. Yeah, go ahead.
Okay, so like with higher learning rates like 0.1, the coordinate updated by top K is far from the one without top K, and this can invalidate the error feedback compensation. So the error feedback is no longer compensating for top K, like in the right plot. Okay, so this is our presentation.
Very good, guys. Excellent. Yes, very good. Very good job. Very good job.
Okay, so
okay, very nice, guys. Also today we went very long, so I think since some of you are also doing some, you're still working on your exams, I don't want to keep you for too long. Let me just know. I'll just call out for challenge 3, and you guys tell me if you have any questions regarding challenge 3. Okay. If you don't have anything, then we discuss it next time. Okay. So group 1, anything regarding challenge 3? I'll give you 10 seconds. 1, 2. Anyway, okay. Group 2. Anyway, group 2. Any question regarding challenge 3? No question. Group 3. Any challenge regarding any question regarding challenge 3? No. Group 4. Any question regarding challenge 3? No. Group 5. Any question regarding challenge 3? No. Okay, guys, since it's still midterm week, I think today we stop here. I think we did a lot today. There were many comments regarding stuff that was missing from the report, and I think because it was midterm week, you guys didn't really have all the time that you usually have for the project, so no problem. Just remember that next time we'll finish challenge 4, and after that we finish challenge 3. After that we have challenge 4, and for the next challenges you can choose whatever team member you want. So hopefully now you're going to choose the people that you like the most to work with and you work with the best. And then as soon as you can choose your teammates, the suggestion is that you start working on the final challenge. And I posted in Slack a proposal for the final challenge, which is a competition that I'm organizing at a nice conference in Michigan. And if you want to participate to the challenge, it's fully online, right? And you can also win some money. So you can try that as a final project. Otherwise, you can ask me about the final project. Okay. As usual, I'm going to be here for 5 more minutes if you have any questions. Otherwise, we'll talk next week. And good luck with your midterms. Okay. Ciao, guys.
Teacher, we're group 3. That's doing
group 3 for challenge. Group 3 for challenge.
2.
Okay.
Yeah.
Go ahead.
Like in the evaluator page, we find out that we lack for some things like no top K and no second order optimization, and I just immediately added up to our report. So I'm not sure that it is right or not. So I think I'll just share the.
No, but again, guys, I mean, don't panic, right? So if you correct it on the final report, then we fix it, right? There's no problem. No,
like here, we've added the top K.
Yeah, good.
And here's the second order.
That's a Hessian one. Okay, good.
Right.
I'll look at the final report, guys. Don't worry. I mean, if there are some corrections to do, I always I correct the final grade, right? Don't worry.
Because we have we've write it in the code, but we didn't show up in the evaluator page.
Yeah. I'll look at the final report after you submit it, and then I'll adjust the grade. Okay.
Okay.
Don't panic, guys. Don't panic. So once you present, right? I always give you some feedback, and then if you fix the feedback by the final report, there is no problem, right? I'm just here to give you some feedback. Okay.
Okay.
So you already had it, right? Or did you run it while we were talking?
Yes, I've run the training while other group are talking.
Okay. Yeah, because Good. But again, don't worry. I mean, just do a good job for the final report, and then I'll change the grade.
Okay.
We're not here to punish anybody. Okay, so we're just here to provide feedback. Okay, guys. Any other question? You let me know. Otherwise, we synchronize next week. Okay. Ciao, guys.